Minute session. Here we go.
Hi, my name is Luke, and today I'll be presenting on CRISPR-Cas9 and the bioethics of eradicating hereditary disorders. A little bit of background about me. I'm a junior at Washington State Biochemistry and Medical Humanities, and I have a research focus on biochemical foundations and primary experiences with healthcare disparities. So this is my first foray into sort of ethics and philosophy. So if I get anything wrong, please forgive me. This is a quick little outline of what the presentation is going to look like. I'm going to first go over the paper, and then tackle the three main lenses that I focus on throughout the paper. The first being a biological and technological perspective, the second, deontological lenses, and then a utilitarian lens afterwards. And then I'm going to follow up with some conclusions, and then have time for the commentary and Q&A. So a quick overview. I elected to use these three perspectives just because I believe that they provide a pretty comprehensive view of the issue at hand. With my biological and technological perspective in the paper, I sort of illustrate the current landscape of CRISPR-Cas9 implementation, sort of the outlooks of the current legislature, as well as a brief history of the technology itself. When I go into the deontological view, it's a lens of normative ethics for those of you who do not know. And I sort of balance what this sort of view of this topic looks like. And I do the same for the utilitarian lens. I chose these two lenses because in a lot of ways they can contrast each other in terms of deontological is absolutist views and utilitarian is more using a means to an end. So because of my unfamiliarity with a lot of normative ethics, I thought that this would be the most. So going into biological considerations, I'm going to give everyone a brief history of CRISPR-Cas9 evolution. This is like my bread and butter, so I'm trying to make sure that everything is clear. Basically, in bacteria is where this mechanism was discovered as a sort of defense mechanism from bacteriophages, which are viruses that specifically attack bacteria. And so there are three main components: CRRNA, tracer RNA, and the Cas9 gene itself. And so these sort of work as a memory bank. So it recalls what sort of viruses and bacteriophages have been attacking this bacteria, and allows it to sort of signal out those specific, genetic sequences and cut right where they are. And so that prevents replication, essentially, is a very strong defense mechanism. However, in lab, this has been isolated by two scientists, Jennifer Dwadna and Emmanuel Charpentier, and really effective to be a single construct called sgRNA, or single guide RNA. And that actually won them the Nobel Prize in 2020. And so with this new discovery and the ability to really make this mechanism super precise, the natural extrapolation from this is sort of the implementation to animals and eventually humans. The high specificity allows for a lot of treatments that was otherwise seemingly not even a possibility, to the treatment for Duchenne muscle dystrophy, sickle cell anemia, or even sort of the elimination of hereditary diseases or probabilities for hereditary disease, which is what my paper tackles. So next I'm going to go into a little bit about the mechanism to see how two main repair mechanisms from this complex are used to sort of induce the changes that are being proposed by a lot of scientists. So this CRISPR-Cas9 complex is designed specifically to target genes that have a known function. So it cuts at these genes and can go about two specific repair mechanisms after the cut. One of those is called NHEJ, or non-homologous end joining. And essentially what that does is silence these genes and can eliminate. So if we're talking about sort of proclivities to heart disease, cancers, that can be used to sort of silence that. In 2018, scientists, or Chinese scientist Dr. He Zhanghu, used this to edit children of parents who had HIV and was able to eliminate the HIV appearance in the children altogether. In the other mechanism for repair is called HDR, homology-directed repair, and that's inducing a new functional gene. So in sickle cell anemia, there's a mutation that essentially makes the gene a little bit different, and it leads to a lot of negative syndromes and side effects. And so this HDR can be used to sort of induce the correct gene and fix it. And so I think that a common sort of conclusion from this, as I presented in my paper, is sort of like, wow, this is incredible. There are endless possibilities with this technology. But I think after considering sort of the downstream ramifications of widespread implementation of this, we sort of get to the question of not only what can we do with this, but what should we do with this? When we talk about eliminating certain biological predispositions through manipulating genes, we're really threatening a sort of biological diversity downstream. And we don't really know what the effects of that are. In lab experiments, when we're modifying the genes with rats, oftentimes it comes with accompanying side effects that were previously sort of unpredicted. And so when we're going about from a technological standpoint that is not fully perfected yet, that's the main reason why a lot of legislature actually bans this in human embryos. So now we're shifting to the deontological lens. For anyone who doesn't know, deontology is also known as Kantism and prioritizes a universal code of ethics and prioritizes rationality. It focuses on the categorical imperative. And I like to think of it as a tripod. There are three main maxims that I found. And one is to assume universal law from your actions. The next is to treat humanity as an ends to itself rather than a means to basically obtain something. The third is to prioritize autonomy and acting as if your own actions dictate the law. And so sort of based on that rough definition, it generally takes a more absolutist view as saying, well, if this is ethical sometimes, then it has to be ethical all the time, and vice versa. So when I'm applying this to my paper with CRISPR-Cas9, I think the main argument that I recognize is sort of the mission to correct hereditary defects really presents a slippery slope. A Pew Research study in 2018 showed that 72% of pollers agreed that changing genes to sort of mitigate or even eliminate predispositions to disease was a good thing. But 80% opposed using the same technology to increase a baby's IQ. And I think that presents sort of the duality of this argument. We recognize that it would be a great use of the technology to sort of get rid of certain predispositions to very negative diseases or any sort of health defects, but we don't really have a strong and clear-cut line as to where it edges from potentially using this technology to better society or using it to give your children a step up on society. And because of this, there's another argument that's presented that offers the further stigmatization of marginalized groups. Obviously, given the American healthcare system, this would most likely not be a free sort of service. Because of that, it really presents us with a future that is even more stratified in terms of socioeconomic class, based on sort of steps up you can give your children even at birth. And I think that is sort of reiterated with the lack of concrete standards for what constitutes a quote-unquote negative hereditary trait. When you look at certain fields, even of study or work, like there are a lot of different traits that can be considered good. And I think deontological views would say that it's violating the child's autonomy when the parents make the choice of sort of shoehorning your child into one field or another and saying, this is what I want and this is good. And so with deontological views, it sort of offers up saying that it's not ethical to implement this just because we sort of see absolutism as a safety net rather than presenting more freedom. And then the next ones that I consider is utilitarianism. It's also known as consequentialism, and basically says that as long as the ends justify the means, as long as we present the most good for the most amount of people, something is ethical. And that's the very fundamentalist view. I understand that modern but my application to it, sort of the questions that it raises are what constitutes utility and what is essentially what is the best for all people. We see that proponents for the implementation of this technology would really argue that sort of the funds that are utilized by the US government, $59.4 billion each year as reported by the Social Security Administration, that can be reallocated to essential services such as education or even public health. And another recent study showed that almost 12% of family income can be dedicated to additional services required for children with disabilities. So utilitarian might argue that using this technology to sort of eliminate those from the start, that might be a way to generate the most utility overall. So some conclusions and essentially what the verdict is from my paper. Still in progress, but what I have so far is sort of recognizing its relevance in the American health system. We're really prioritizing where the American health system really prioritizes the production of money, and because of this, like the essential stratification that is presented by the implementation of this technology, and the recognition of using a strict moral lens, either utilitarianism or deontology, as not really the true answer to either of these problems. I think also it's important to recognize the loss of diversity in both genetics and culture that can be presented through widespread implementation of this. A lot of hereditary disorders, such as people who are deaf or those with Down syndrome or any sort of other hereditary disorder, end up forming their own very rich cultural communities. Even in St. Louis, we have 3 schools for the deaf, and there are quite a few deaf clubs. I think that's really an important part of our society that we can't just neglect in terms of saying, oh, we're just going to wipe this out because society sees as negative. And I think another sort of factor that can help us justify why this might be unethical from a biological perspective is sort of the uncertainty and long-term consequences. I think had the technology been perfect, had we been able to recognize, oh, these are the exact future downstream consequences, it might simplify the argument a bit more. But given the current state of the technology and our uncertainty in sort of the future, I think it validates current legislature in saying, okay, we need to make sure that we take a step back before we start human trials. We need to make sure that we consider all these possibilities and also consider this not just in a scientific lens, but also from a philosophical lens. That's all. Thank you.
Now we'll hear 5 minutes of commentary from Eleonora, who's coming to us from STLCC.
Hi, everyone.
Hi.
So thank you, Mr. Kim. So as humanity progresses in technology and takes further steps in science, scientists undoubtedly can experience a sense of adour and discoveries. They can make everything possible. How cool would it be to have 6 hands, like one on the phone, one writing something down, one holding the keys, no need for pockets, right? However, even with promising innovations and good intentions, there may be consequences that entire society and the globe will face, willingly or not. However, ethics is a filter we should utilize, which innovations should be applied to people's practical lives. Mr. Kim's papers examine deontology and utilitarian theories in view of growing concern for gene modification. The ethical concerns around gene editing are significant. We live in a material world, and our conscious and unconscious minds in our world to live are closely connected to our body. Mr. Kim has emphasized that genetic differences must be considered wisely. Which genetic traits are dangerous? Which should be left as they are? And who will choose? Who will decide? It would be beneficial to determine the effects of gene editing on different socioeconomic layers. Ethnic groups, races, and people of various national, religious, and cultural backgrounds guarantee a difference in genetic code, income, lifestyle, and mindset. Religion is a very important part for many people, and some religions do not allow gene editing. Christianity and Islam, for example, are the religions that prohibit the use of gene modifications, and groups as such will get social disadvantage, possibly with weaker health and bigger expenses on health and procedures. In the near future, mostly affluent families will be able to afford gene modification, as Mr. Kim said. Since the technology is still in development, there can be many unpredictable effects, and this prospect is costly. It supports the claim made by Mr. Kim that it reminds us more and more about eugenics, which exacerbates racism and inequality. Thus, the idea goes against utilitarianism, which says that the majority should get advantage. However, it is similar to other innovations initially introduced to the wealthy class, but becoming more affordable through further developments. The consequences of gene editing are that there will be complex international relationships between countries willing and capable of administering gene modification practices on larger scale and those that aren't. As Mr. Kim has said, there will be need for legislation, agreements, and that organizations that can monitor, regulate, and limit the powers for genetic modifications. Nevertheless, different nations and states will pursue various goals. People with different mentalities will undoubtedly pursue different things, and it will take collective effort to organize the law, thus requiring compromises, high flexibility, and endurance from society to put limits on this constantly changing field of science. Deontology as a theory is inflexible on the practice of rules and imperatives. Deon in Greek already means binding, and moral problems and ethics are not mathematics. It's not 2 + 2 = 4. It is more complex, subjective, and debatable, but maybe strict deontological rules are exactly what we need. The National Library of Medicine writes, unlike many other ethical theories, deontology does not focus on the consequences of individual actions. Personal emotions do not matter within conscious deontology because Kant believes humans do not allow rational control over their feelings. Instead, the intent behind chosen action is of far more importance. Thus, deontology proponents judge actions based on what most people consider to be morally correct, regardless of actual consequences. End of quote. The intentions behind this technology are praiseworthy. To undermine the predestined bad health that can make a person miserable and die early. Yet the executions are likely to cause more harm than good. Nevertheless, saying that genetic modification and engineering is unethical is like attempting to fight the concept of popularity. As the upper class will adopt this practice, others will strive for it as well. How will we know when to stop if we don't put the decisive limits? How do we ensure that our initial intentions don't get lost in the prospects of science? Gene engineering is limitless. We have only started to explore it, and it can transform societies forever. As I love to say, the bigger the stakes, the bigger their reward. You must decide whether to accept risks or reevaluate the benefits. How do we collectively decide who should be valued more? The healthy with stability or the potential of people without the hereditary disease?